All right, so it's page 41, and so the top part's just review. To me, this is the most important piece because it does explain what kinetics is. I'm like crooked, but so kinetics is just studying the rate or how fast the reaction goes. So we're looking, yeah, at the speed of a reaction, a chemical reaction. So does anybody remember what any of the three things were that make a reaction go faster or affect how fast it goes?
Temperature.
Temperature. Yeah, I'm gonna put that as number 2 because that was where I put it last time, but I don't care what order you put it in. And I am gonna be asking you, I always ask this question on the test, to give me the 3 things and to explain why. So, I mean, you guys have, it's easy because you have a thing there, but temperature, whenever you explain, the rate has to do with collisions of the molecules of the reactants. So we need the reactants to collide. So temperature increases the jiggles, the giggles, the wiggles, whatever you want it, the kinetic energy. So if you have more jiggles, you're going to get you're going to get more collisions, so greater frequency and force of the collision. So again, anytime you change the temperature, we can add that here because it's something that we're going to be doing on the last page. Whenever you increase the temperature, you increase K. So K is a constant. We're going to do the chart down here, but temperature changes the value of K. So that was like density is a constant, except it changes with temperature. Anybody else remember another thing that changes the rate? Well, it starts with, we'll do concentration. So everybody concentrate. Or you can write down what I just wrote down. So the concentration of the reactants. There is a way that the products could influence it, but I'm not going to go there. I cut that question out. So real quick, the homework set, I posted my answer key from last year and the past 20 years. There's 2 questions I cut out, but they're on my answer key, but they're things that in all honesty, I don't have the stamina right now. And I know you guys, this environment is kind of draining. And so I put a disclaimer in your homework that this question has been deleted, just draw a picture, but it's on my answer key. But the concentration, if you add more stuff, you're gonna have more collisions. So if you're, like Saul was a great example right now, he had 2 people in his life and now he has 3 people. And so there's more stuff going on. So you just increase the probability that things are gonna collide. And then another comment here with concentration, I'll write it up above. There are other things that influence the concentration, so you could add more of the reactant. You can also change, so this can be, you could also, if you decrease the volume, that will increase the molarity, right? So that's, you could just increase the amount, the moles would also increase the molarity. So if you add more of it, and then there's actually a third thing, and they all are concentration. They all affect the concentration. So like when I asked for 3 things, these are not 3 separate things. So you could also, if you increase the pressure, because when you increase the pressure, that will decrease the volume, and that increases the concentration. So pressure will actually have that effect. All right, and then the third thing, which is actually huge, this gets like lots of stars, is a catalyst. So you can draw a cat for those of you who are good at drawing cats. And what a catalyst does is there's a couple ways I can explain this. It orients or aligns So every collision is perfect. So every collision makes something happen. And again, the other night I gave like a simple example, like if you're in a parking lot and, or you guys have all done it, just walking down the street and you're talking and you bump into somebody and you're like, oh, I'm sorry, nothing really happens. This is a catalyst always makes that bump happen, so something like you would break something. So it aligns the particles so every collision is perfect. And in doing that, it decreases the activation energy. So I have to make another quick disclaimer because I realized today I made a huge mistake in the first lecture. A catalyst, though, is, this part I said correctly, a catalyst is the only thing that lowers the activation energy. The mistake I made, so I actually want to go back to the first page and fix the very first page of the notes, if you have them, on page 37. At the very bottom of the page, when I drew the diagram, I read it correctly out loud, and then I drew it wrong on the board because I'm not in my element. This is endothermic, and I drew an exothermic. So later in this lecture, I'm going to go through both of them, and I will draw them correctly. So on Tuesday. So in lecture, what is this? Lecture 8A. In lecture 8A, I drew it exothermic. I said I was doing endothermic, but my brain and my hand are not doing the same thing, apparently. But I'll correct that later. I just wanted to make that comment for anybody listening, or when you're all listening, that I do know I messed up. And you guys don't know it yet, but now you do. All right, so those are the three things that affect influence or reaction. I want to go through one of these charts, and the first page of your homework is dealing with these charts, and these are looking at our first situation, how concentration changes the rate. And the easiest thing to do, you want to look, so we're going to compare reaction 1, experiment 1 to experiment 2. So the amount of fluorine doesn't change. So you want to look where only one thing changes. And so if you look for experiment 1 to experiment 2, we triple the NO2. And in your calculator, that goes up by 9-fold. And I know that because I know where I'm going with this, so I know what I'm looking for. But you can always take the second number and divide it by the first number. So if you take the 3.67 and divide by the 0.41, if you can't see with the ratio, you get like 8.95. So it changed by 9-fold. So basically, if we took NO2 and I tripled it, you get a 9-fold change. So the question is, 3 to what power would give you 9 times the rate? That's what we just did. So if you took the NO2 and you go triple it, that's going to be 3 to the 2nd power. Will give you 9. So the rate became 9 times what it was. That 2 is the order of the reaction. Again, the vast majority of things are first order. And yeah, we'll come back to the second order. So now we're going to look at the fluorine. So this is the easiest way for me to kind of diagram it. This is very different from other things that we have done, but the students always get it. And it's just we do a number of practice, and then on the midterm, pretty much everybody gets it. The students who don't are the ones who don't come and ask a question. So if you're having trouble with it, next week, the Tuesday office hours, because this should be the question on the exam. And getting this step right is important because all the rest, you'll have all these other steps with it. All right, so for the fluorine, I want to compare the first one to the third one. So my question for you, and for all of you when you watch this at home, is why didn't I compare? I want to compare when I change the fluorine, so I double it, but why didn't I compare the second one to the third one? Why did I pick to choose to compare the first to the third?
Is it because
You
of the
only,
rate?
go ahead.
Is it because of the rate?
You do it, no, but it is because you only want one thing to change. So you have to look at the NO2. And if you look at experiment 1 and experiment 3, the NO2 doesn't change. Only the fluorine changed. So you only want one variable to change. So when I doubled the fluorine from 1 to 3, without any change happening to the NO2, my rate doubles. That one you guys can see, 0.41 times 2 is 0.82. So I get double the rate. So if it's a straight exchange, if you triple it and you get triple the rate, that means it's first order. That whatever you did, you got the same thing. If you cut it in half, and the rate would go to 1/2. So that is called first order. For the NO2, it's called second order. And then something I didn't mention the other day is this is considered third order overall for the good of all of us. So they would say it's third order overall. Writing the rate law, which is step F here, you always start out by saying rate equals lowercase k. So they're always going to start by saying that rate equals k. And then you do brackets. Now, if you do parentheses, I'm okay with that. But the brackets mean that you're putting the concentration in or whatever our units are. And we take our first reactant, the NO2. And this one we know second order, so we say to the second power. And then we put a second set of brackets and we put the fluorine in there, just a symbol for fluorine. And that would be to the first power. You can leave the 1 off because it means it, or you can show it. That's like a personal preference of each student. Some students like to show it because it means they know they finished it. And some students just leave it off because it's a 1. It's like when we balanced equations, some of you always had to show the 1s because that's how your brain thinks. You need it to have a number, and some of us can leave the 1 off. All right, everything has its own unique rate law. The rate law does not change from a temperature or a catalyst. Nothing's going to change the rate law. That's true for whatever the reaction is. And so given a chart like that, the homework, we did 2 the other night, and the homework has 2 more, and then probably your lab will have another 1 or 2, because it just takes practice. You just do them, and yeah. All right, so determining the value of K, this is now an algebraic equation that is true for this set of data. You can set in any set of data you want. Sorry, I'm going to use the first set of data. So for the rate, I plug in 0.41. My units, it tells you in the chart, is molarity per second. And that equals K, which I'm solving for. And then I'm using my first set of data. My NO2 is 0.20 molar. And I'm going to square it. And the fluorine is 0.10 molar. Now, some students, yeah, we need, the units are the hardest part. They're a 1/2 point, so don't lose sleep over them. If the units are confusing you so you can't do it, it would be best if you kept the units in. We're going to divide, right, by the 0.2 molar squared and the 0.1. So they'll move over and we'll solve for K. And this is a really awesome question. I think Edward asked me the other day, why do I suddenly have 4 sig figs? I don't know. The answer should only have 2. So really we should say that K equals around 100. The units, one of the molarities is going to cancel. So you're left with a molarity squared, but it's in the denominator. So we say m to the minus 2 because it's when it's on the bottom, that's a negative exponent. And then the seconds is also in the denominator. So that's why it says s to the negative 1. So you can write it like that. I'm going to show you the other way that you can also just say 100 over molarity second. I want to show you one other way because some of you do use the book, which is awesome. They do a really good job with this chapter. Molarity, if you remember, right? Molarity is moles per liter. So if the molarity gets flipped to the bottom, this is the same as saying, I'm sorry, that should be molarity squared. I said it and I lost it. This would be the same as liter squared over mole squared seconds. Now some of you are going, what the heck did she just do? That's seconds, sorry. My handwriting got faint. It's just when molarity is flipped over and squared. And again, it's because I gave you, I was able to post the book we used to use, and they would show the units like that on the answer key, and I find it a little bit odd, but you can show it. I prefer the first way or the second way. All right, we're going to do this where we're going to determine the rate for the fourth set of data. So you're going back to your rate law. So whenever you have these, you're going to have multiple steps, and we just plug in. So rate is what we're solving for. This K is true for any of these problems. So M2 seconds, and then we just plug in our data. The 0.85, remember you got to square it, and 0.35. And again, I'm getting the data from here in the fourth row in the chart, and we're just solving for the question mark. And I'm going to assume that we get my answer. A question that usually comes up, you probably, if you punch it in, I can do it real quick. You're probably going to get not quite my answer. Yeah, you get 25. And that just has to do with rounding. Like I will keep my numbers in my calculator, and what I've noticed is some of you do that, and so I probably solved this keeping it as 102.5 blah blah blah. That's not a big deal. If you got 25, 26, 27, we're in the same ballpark. The units, you can tell how the units cancel. The molarity squared will cancel, and you'll be left with a molarity per second. The other way you can show this unit is you can say moles per liter seconds. It's a preference thing. I honestly don't care, but it is a frequent question I get from students. So I'm trying to anticipate questions that you guys might have who are watching this at some random time, probably Saturday when it's pouring down rain. And all our gardens will be so happy. Is there questions? You guys ready to move on?
Oh, I did have one for 100 liters over moles second. Is that 100 liters squared? Is that marked right above it?
Yeah, no,
It
that's
is
liters
okay.
squared. Yeah, my paper was on something and I hit a bump. Because it's molarity squared upside down. Does that make sense? So it would be liter squared over mole squared. You don't have to show the units that way. That usually freaks students out, but the book does it that way, and I know a couple people like to read the book. Is there any other questions? Or we're gonna move on. All right. So this page, we're on page 42. This is the page we usually spend an hour on. And this is what I was saying, I cut out of the homework. But I still want to go over it so you know the relationship. And there's a lot of stuff written on here, and we don't have to do all this work. Zero order reaction, when you rearrange all this stuff, it comes out as a relationship that the relationship between time and concentration is linear. So it's a linear relationship between time, little t is always time, versus the concentration of A or whatever you're talking about. When it is first order, so that was for zero order. If it's first order, and again, first order is the most important one, most things are first order, it is a natural log relationship. It is not a linear relationship. And that was the one I talked about, that the decay is not linear, it's a natural log. A linear relationship, we would see it, right? So, and then down here, again, the relationship is not linear. It's an inverse of the concentration versus time. And that is second order. So that's that in a nutshell. What we used to do is we could graph each one of these on our calculator, and you could take any set of data and figure out if it was zero first or second using your calculator. But that usually involved me coming around and helping everybody and having you guys help each other, because we'd figure out who had what calculator, and I don't see that happening. It just shows you a use for natural logs and for a linear relationship. But this question here, and this one that I just put there, what is half-life? That is something we're going to go through. There is a lecture Tuesday, and that is on nuclear chemistry and nuclear decay. And half-life is how long for half a sample to disappear. Decay, decompose, what depends on the sample. When it's a nucleus that's falling apart, we call it decay. When it's a compound, we call it decomposition. So that's the difference between those words, and only a chemist probably would care. But half-life is the time for half of the sample to decay, half of the sample to disappear. So nuclear chemistry is always first order decay. If it's zero first or second, that never changes no matter what. If you go to Mars, if you go to Jupiter, yeah. All right, we're only going to do half-life with first order decay. And so the equation I showed you the other day was, it's this equation up here. But for half-life, you just put it in as natural log, sorry, I'm going to change that to of 1/2, that's a 1, over 2 equals, so negative k, and then it's t 1/2. That's the symbol for half-life. It doesn't mean times a half. It just means half-life. So that's like a subscript 1/2. That is a common question students will ask me like 2 weeks later, that they just didn't understand that it was just a symbol. All right, so iodine 125 is actually radioactive, and it's what they give people to study thyroid or for thyroid treatment. So this 6.8 is the beginning treatment. That would be A sub 0. So sub 0, this lower number here is the start. And then the upper number is at some time. So then tells us, okay, after 1 week, you have 6.3. So that 6.3 is A sub T. And it wants to know what the half-life is. So we're going to go with our formula here. So this is going to be my step 1. I didn't read my question before I started writing stuff. So AT over A0 equals negative KT. And the AT is always on top. So that's your final, 6.3. And I do want to remind you of something, and I'm aware of it, and I try to avoid it on your test right now because you guys are printing it yourself. Some of your printers don't print my symbols correctly, so the micro doesn't show up for you right. It will just show like a little box, but you can always go back and look at the original picture on your computer screen and it would show the symbol correctly. All right, the units, when you're doing decay, first order, do not matter. So as long as they are the same. It is a ratio of final over initial. So as long as they're the same unit, they can be any unit. They can be pressure, they could be concentration, they could be radioactive millicuries. So the micrograms will cancel. And I'm going to change my time to 7 days. It showed 1 week, so I'm going to make it as 7 days. I don't like week as a thing because it's a vague, well, I guess it's 7 days. All right. So go ahead and punch it in, or you can just wait, or you can fast forward.
Oh, Miss Sherpa.
Go ahead.
When we draw the, I can't remember from our last class, so what the U stands for, what the U is. But do we have to draw it like you draw it? It can't just be drawn like a U.
For the microgram, you can make it's
Yeah.
a U with a little tail at the beginning. You can also write MCG.
That's right. Okay,
is that what you were thinking? That most people now write MCG. All right, you have to, K is always a positive number. The negative, right, you would divide by negative in the 7 days. And the unit, this is what I got for my value of K. We're not done yet. This was our step 1. You want to find the value of K. And then we're going to take this number of K and plug in here to solve for the half-life. So you then would just take the natural log of 1/2. And that's going to equal negative RK 0.0109 per day and times the half-life. So we can punch in. Yeah, you should get around 63 days, 63, 64 days. And please just make sure you number your steps, especially if you do something like I did, where I did them in a backwards order. You can use an arrow to show how things are flowing. There is a way to combine this into one step, but I don't see an advantage. I usually see students who do that end up getting it wrong in a test situation, because even though you guys have the luxury of being at home, several people have told me there's more distractions at home, that they don't find the time to focus. And so that's the hardest thing. I know for my son, that's been really hard on him. His testing ability has definitely gone downhill because our home life is a very different environment and people are coming and going. All right, this question right here, does your answer make sense? You are going to be asked that. It's on the worksheet, it's on the homework. So we did one the other day, and this one's actually a really good example because it's a different ratio. We did not go through a half-life. In 7 days, we were nowhere. A half-life would mean if we started at 6.8, we would be at what after 7 days? I'm sorry. Once we go through a half-life, it would be 3.4 micrograms. So we have not gone through, we went through like a fraction of a half-life. So the half-life needs to be, that was our answer, that our half-life was 63 days. And so you would want to word that somehow because we hadn't gone through a half-life yet. So only a fraction of a half-life. So only a small fraction, we can write that, only small fraction of sample decayed. Whoops. Half-life is longer than 7 days. And I mentioned that because the one we did the other day, it went through like 5 half-lives. Aaron might remember because he had asked me the question. And so a lot of it had already decayed. So sometimes you'll only go through part of a half-life, and sometimes you'll go through quite a bit. All right. First order decay, absolutely. So the question on the first page with the chart and figuring out the order, you will definitely see that question. You will have to use this, doing first order decay and half-life, and explain, does it make sense? This question number 4, just cross it out. We're not going to do it. I'm hoping it's not on your homework. Okay, maybe it is on your homework. Maybe we should do it. Oh, I don't have your homework with me. It's in the other room. Actually, let me go ahead and do it. We're not going to work it all the way out, but I want to show you. Second order decay, it tells you in the problem, it follows second order decay. Here's your equation. So that's simple enough, right? 1 over the final concentration minus 1 over the initial concentration equals K times. The T is time. Lowercase t always means time, and capital T means temperature. This is, again, second order decay. And it gave us the value of K. It gives us a temperature. Temperature we can ignore because it didn't change. And it wants us to find time. So here's our initial, A sub 0. Here's our final. And I decided, again, I'm sorry, we're going to do this problem. I'm going to at least show you the setup because I honestly can't remember what the homework has in it. I did post it. One of the things I want to point out with this question, okay, I gave you K is 30 liters per mole minute. K, a couple things I want to point out. Okay, we're solving for time, and you should get around 3.3 minutes. The units for K are going to always be funky, just go with them. The time unit in K has to complement your time unit. So K will always be per time, so per minute. So when we solve, our time will be in minutes. And then second order decay is not a ratio. So these must be molarity. First order decay, we did not have to switch to molarity because it's a ratio. Second order decay is not. But it's just plugging in your calculator. But I'm going to move on just because I don't know how much time I have. This is the piece. We're not going to actually do the graphing, but zero order, they're all time on the x-axis, and zero order, the y-axis is concentration. In first order, it's natural log of the concentration. In second order, it's 1 over the concentration. It's kind of everything that was up here on top of the page. So concentration, natural log of the concentration, 1 over the concentration. So we would make 3 separate graphs, and we would figure out which one was the best graph based on which one gave the best line. So if you compare the R's, R is something called correlation coefficient, which you may or may not have heard of. Can you guys hear me? Okay. The slope, the absolute value of the slope is your K. So it's a graphic way, it is a graphing way to figure out the rate constant. What you guys would need to know is if the only question you might see in the homework or on a test would be, in a second order reaction, what is the relationship between time and concentration? And you would say, well, time is related to 1 over the concentration. That's all. And unless you're going into kinetic stuff, don't really need to worry about this. Question number 3, we're going to see that again. It's a really great application of natural logs. And if there's no questions, I'm going to move on to page 43. All right. Page 43 is all new. This is something I did not go through. Page 44 is just more temperature stuff. So this is the catalyst. So this is really cool. We're not going to do any calculations on this page, but this is something that's very unique to kinetics. Reactions, it's been a lie that I have been carrying through. Reactions do not happen in one step. Reactions happen in multiple steps, but they're happening so fast. We're talking like femtoseconds. And so what people get doctorates in chemistry, I'm a biochemist, so I didn't do this. They will do their whole PhD or their whole career trying to figure out these mechanisms. So they're called a reaction mechanisms. And it's what it says. Most reactions, when they collide, the NO2 and the fluorine collide, they make this guy, which is a really weird thing, FNO3. And they make fluorine. That is a fluorine without a negative. That is a free radical. That free radical is going to react. And it immediately reacts with the NO2, and we get this. So the F, the second thing I circled, is called an intermediate. It is something that we make in one step, and then we use it up in the next step. It's on different sides of the arrow. And so the arrow is like an equal sign, and so we can cross it out. So when I ask what's the overall equation, anything that's on opposite sides of the arrow, we're going to reduce, cross them out. The NO2, we add them together, so we get 2 NO2s plus a fluorine, and we make 2 probably very toxic compounds, so FNO3 and FNO2. And for those of you listening, there's a couple of you who didn't give me topics yet, so I'm hoping you're going to email me. Like when you see this, you'll probably have gotten an email from me already. So yeah, that's the overall. We just add the two together, and anything that was on opposite sides, that was the same. It should be balanced. So we have 4 nitrogens. Wow, it is not balanced. I'm sorry, we have 2 nitrogens. We have 4 oxygens. Something is not right. You know what? I just realized what's wrong. Nobody, you know, this is usually late at night and we're all tired. This question up here, this should be FNO2. That is like a typo in this, my notes. That has been perpetuated for eons. That should say FNO2. So these should, there is no, that's why I circled that. I'm like, that is not the real thing. All right. So many typos. You can't get rid of me now. It's been 8 weeks. All right. So again, I'm sorry. Hopefully at the end, the next one's good. So this should have been FNO2 and another FNO2. So 2 NO2s plus an F2 gives us 2 FNO2s. The thing that cancels out is an F and the F. So what I was trying to say now that we have it correctly done, is this did not happen in one step. And logically, it would not happen in one step because there are 3 reactants. There are 2 NO2s and there's an F2. The likelihood of 3 things meeting together in time and space at the exact same instant is so infinitesimally, it's like so improbable, it's not going to happen. To have 2 things collide at the same moment, yeah. And so that's why it happens stepwise. All right. The rate law. This is the whole point of reaction mechanisms, is it's a cool way to find the rate law without having to do the chart we did. You will always be told which step is a slow step and what is the fast step. Almost always, the first step is your slow step. And again, when it's saying slow, we're talking like a nanosecond versus a femtosecond. So this is moving in time frames a billion times faster than you and me. We're in like ultimate slow motion, clumsy compared to this. And chemicals, a femtosecond is like an infinity time compared to how light moves, how vibrations move, which is really how your body communicates, in case you didn't realize that. So this whole molecular model we've made for how our body communicates is just somebody's BS or belief system. It's really nice, but it doesn't really work. That's why acupuncture works so well, because it uses vibrations. All right, the rate law is the slow step. Stoichiometry. So stoichiometry means the balanced equation. So we write rate equals K. You always start like that. And then we put a bracket and we have NO2. We have just one of them in the slow step. And then we have another bracket and we have fluorine. We have just one of them. That's it. So the order equals the coefficient. Of the slow step. Since the coefficient in the slow step was 1, the order is just 1 for both. The intermediate was the F, so it was a free radical. And the molecularity just means how many things are colliding. So how many reactants collide in each step. So for this, each step has 2 things colliding, so we call it bimolecular. Again, the vast majority of things are going to be bimolecular, saying 2 things collide. If only one thing was present, it's called unimolecular, and that's going to show up in the next one. All right, questions? So I'm going to do this correctly today because it's Thursday. So we're going to do the energy diagram, and I am going to do it for an endothermic, and I'm going to show it to you correctly, but there's going to be an extra twist to it. So you make your 2 axes. Your lower axes, you don't have to label it, but this is the reaction moving in the forward direction, right? So just like it is up at the top of the page. And over here, this is called an energy diagram. This is energy. In chemistry, we usually think of that as a heat change. Endothermic means into. So it's going to absorb heat, which I absolutely know. And the other day, I exited the heat. So it's like your bank account. Your reactants are here, which is the NO2 and the fluorine. And at the end, you end up with more than where you started because it's going into. So the other day I did it and I exited. And we do an XO1 down at the bottom. So my reactants, I'm sorry, my products were the 2 FNO2s, right? All right. Now we're not going to hook them up. We're going to connect them, but not with a straight line. But there's a catch to this one. It's not one hump. You're going to always have, you're going to have 2 humps. The 2 is the number of steps. So when we do this one down here, we're going to have 3 humps. The slow step is a huge hump. That's what it means to be slow. So exaggerate it. And a hump means it goes higher. It's like your bank account went really high, and then it came down, and then you have a little hump. So this is step 1. That's step 2. That's all it is. All right. You can make your hump as large or as small as you want. It's a hill or a hump, whatever you want. All right. From the beginning to the end, the difference is your delta H, and it is positive because it's endo, which means positive into. It's just like your bank account. Somebody gave you a big deposit, then you spent some money, and then you got a little bit of money back, and then you spent some more money, and now you're there. From the beginning to the top of the hill is the activation energy. That's the energy to get it going. How much energy did we need to get it going? It is technically called E sub A1 because it's step 1. If you take the second hump, that change there is E sub A2. It's just a little change. So it's like you're on a roller coaster, you're going way up high, and then you go down, and there you go. That's it. So, questions? And keep going. We're going to do the second one. And in your homework, you have 2 more of these that you gave to do. And you'll have one of these on your midterm. And you'll have these questions to answer. So, let's do it. Overall reaction. If you guys have a question, stop me. Those of you at home can just pause and do whatever you want. So, we actually kind of do a lot of these steps at the same time. We want to find things that are not going to be in our overall reaction. So these 2 chlorines, they are Cl, not Cl2. They are intermediates. So see how I made them, and then I use them in the next 2 steps. So they cross out. And they will go here under my intermediates. You can just write, yeah, so 2 Cls. Does anybody see the other intermediate? There is 1 more intermediate in this reaction. And that is the carbon with the 3 chlorines. They're just incorrect formulas. So the reaction happens, they're colliding, and they're not colliding perfectly. So then they collide again. So the CCl3, we make it, and then we use it up. So the CCl3 is my other my other intermediate, and so I can cross it off. So again, it's something that's made in 1 step. It is not, it's usually used up in the next step, but it could be 2 steps later. And then our overall reaction, we just add it together. Anything that's on the left side, we put over here. So we have Cl2 plus CHCl3. And we end up with HCl plus carbon tetrachloride. And my equation's balanced this time, so we're good. the rate law. Always write rate equals little k, and then we put our bracket. The rate law is always you look for the slow step. The slow step is, so if we went, this is the analogy I always give in class. If we went to climb Mount Hood, it's gorgeous right now, right? Because it got all that snow and the air is so clean because nobody's driving, and so you can see all the volcanoes there in here. It's really beautiful. All right, so we go to climb, and I am going to be the rate limiting step. I guarantee it. Maybe I'm in better shape than some of you, but initially I might be ahead of you all. But when we get to a certain altitude, I'm going to be the slowest. I've been at high altitude enough to know I will be the slowest. I'm not bragging, it's just, it's not a fun thing. And so we are all attached. Like I've been attached to the people who've taken me to high altitude and by a rope. And the people on that rope cannot go faster than I am going because I am moving so slow. So that's the idea, that this reaction is determined by the rate limiting step. So thankfully we put me first so everybody else can like do whatever they want. The reactant, we ignore the product because it goes into the next step. So that's it. It's a classic first order reaction. The molecularity is unimolecular. So you can just say uni or unimolecular. Like uno. You can say uno. That's a fun game. All right. Joey and I always play it when we go to my mom's. The three of us just play it, and usually Joey ends up on the floor. He's laughing so hard. We have yet to hurt Joey, but you guys have done that, right? That's the one thing that's fun with family, that there is this laughter that happens at a level that just doesn't happen sometimes. All right, we're going to do an energy diagram. I will tell you if it's exo or endo in 221 and in 223. In 221, we did math, remember, to figure out exo-endo. We get to do that again in 223 for those of you taking the summer class. Yeah. So exo means we're going to lose heat. It's exiting. So you start high and you're going to end low. And I'm pretty sure that's what I did the other day. That's what my memory is telling me. So this is, you can also just write reactants and products. So this would have been the Cl2, and we ended up with the HCl and CCl4. We are going to connect it with 3 humps. 3. I call it 3 fingers. The first hump is huge. Make it as big as you want. It's not necessarily wider, it's the height. So we got to go way up, and then we come down. It's like in our roller coaster, and you get 2 little humps. And then you go to the end. So 3 humps, because it's 3 steps. The distance between the reactants and the products, that is, we lost money on this one, and we lost heat. This is heat, sorry. That's our delta H, that's our heat change. We can tell from this there's 3 steps. The activation energy is from the beginning to the top of the hill. So again, that's called activation energy. Yeah, maybe that's why that first video was blurry, because I messed up. Maybe my guardian angels were trying to tell me I messed up. And then you have 2 other little humps. So you technically have 3 little activation energies. So I will tell you if it's exo or endo. I will have you label it for each step. So that would be EA2, and that would be EA3. The overall enthalpy is delta H. And one more step is the catalyst. And my cat must have known I was at the step because he decided to come see me. So come up here, Rocky. All right. The catalyst, what's a catalyst do? It lowers the activation energy. Basically what it gives is it gives an alternative pathway. So again, this is all of us climbing up Mount Hood. We're all attached to a rope and we're going like the really long way to get to the other side. So, you know, the bear went over the mountain, the bear went over the mountain. And so the catalyst is telling him, hey, I got an easier way. You don't have to go over the mountain. You can take a shortcut. You know what? I do have other colors. So we can do a purple cat. That's the catalyst. The catalyst does not change the beginning, does not change the end. So it does not change the delta H. It just gives you a way around the activation energy. And if you want, you can draw a cat on your catalyst. He's like saying, come with me. Kind of hard. We don't have a lot of room. All right. That's my cat on my catalyst. He doesn't, cats are really smart. They sleep all day. They're really smart. We're all doing, going crazy, and they just sleep. And they know they don't have to go all the way over the mountain. Is there any questions? We got one more page, which is temperature. All right. Those of you at home. And I'm going to turn the page if you guys are all ready. You can add your catalyst drawing unless somebody has a question. All right. Last page. So this formula, so again, when you, for your test, you want to have, I would make a piece of paper or a note card and have your formulas, have your notes. So you're not trying to flip through all your notes, try to finish stuff. And if you do your study set and your worksheet sincerely, and I'll be here Tuesday. We do have a lecture after Tuesday on nuclear stuff. All right. So how and why temperature? More kinetic energy. So you're going to increase the jiggles and giggles. So when we meet for real, like usually everybody's sitting in their chairs whenever I do this and everybody's just jiggling and it's so fun. And I don't get to do that this year. So I can imagine all of you at home jiggling as you're watching this part and giggling. My other class has an extra credit. They had a choice, like you guys had on your gas laws, but they're doing telomeres. And one of the ways you increase the length of your DNA is giggling, like being silly. And so they have a challenge. They get to pick one. And I don't think, I'm hoping one person picks it, but it's that every day they have to giggle until they jiggle. And, but no, it's better, Janae, they have to make somebody else giggle until they jiggle also every day for 7 days. And I'm like, oh my gosh, you know how long your telomeres would be if you could giggle until you jiggled every single day of your life? Do you know how long your life would be? So we might do that challenge in the summer. All right. So if you don't like being giggly and jiggly and you want to be like you just want to say KE. KE is kinetic energy, which means things are giggling and jiggling and being silly. And so you get greater, you increase the number of collisions and how hard the collisions are. You can think of your own clever way to say that. I'm sure the book has. So everything's hitting really hard. So it's like an accident at 65 miles an hour is going to be much more devastating and effective, cause much more damage. Activation energy, we talked about On the previous page, that's the energy to start the reaction, to get the reaction. So everything has an activation energy. R is 8.314. I am going to do it as e to negative 3 kilojoules per mole. It is a gas law constant. That's why it gets a capital R. And we're using kilojoules instead of ATMs. And again, EA is the activation energy, is the full name. So the energy to activate a reaction. Won the 3rd Nobel Prize, hooray. All right, so temperature 0 degrees, we get this number. 10 degrees, we get that number. We're going to plug in. So on your homework, you're going to state this formula again. And then we just plug in. So I'm going to put this as my second set of data. I greatly appreciated, that's one of the things with these virtual lectures, you all go back and can watch it, so you can probably see my handwriting better than you did it in class, even though it was blurry some of the time. And I'm extremely grateful because you've all been very kind to all of your teachers. All right. E sub A is what we're solving for. There is a negative here. The activation energy is always a hill. It's never a valley. It's never a dip. So we'll have to, that will factor in when we do the math. You can just write R, or you can write this number. And temperature has to be in Kelvin. So the 10 degrees, my second one goes 283 Kelvin. And 1/273 Kelvin. So simple enough, because you have the formula there, you just pull the pieces in. And I'm not going to spend the time, but the answer is 57. This is a calculator. I would tell you, this is a parentheses, this whole thing is in one parentheses, natural log. Some of you are wonderful putting stuff in your calculator. You're solving for the EA. So you can put all of this in and then move it over. Remember the negative moves? So your activation energy will come out as 57. And that is kilojoules per mole. So it's how big the hill is. Activation energies are huge. These are really large numbers. I know that's hard for you to recognize. So please try it. And yeah, you're going to have one of these questions. So you can see the questions you're going to have is what we did today. So you're on kinetics. You're going to have one of those charts. You're going to have one of these temperature questions. You're going to have the first order decay, that half-life question. And you're going to have the mechanism. I think that was the 4 things we did today. So there you go. And then that would be a part of the test. And then you'll have solutions. And let's go ahead and do this. This is part B, so we're using that activation energy. So I'm going to make this my K2, and I'm going to solve for T2. So I'm going to make that number up there, 3.74 e to the 4th. Oh, I changed the units on us. Get rid of that M. It should just be per seconds, which is the same as S to minus 1. It doesn't matter which set of data you kept, just be consistent. I know my EA is 57. I'm just going to write R because I'm tired. And you're solving for T2. It will be in Kelvin, and then you go back. Then we're going to do one more piece with it. So this is where I usually spend 20 minutes in class, and some of you take a break, because some of you are really good at putting stuff in your calculator, and some of you are not. I want to skip to there is a C that didn't show up on mine, which means it's not on yours. And by the way, the far side says, my brain is full, can I leave now? Because that's usually how people are filling in the 8th week. But you guys can leave at any time because you're at home. So it's actually, there's a lot of advantages to this. I went on a walk with some of my colleagues today that live near me, and that's what they were complaining. And I said, yeah, but look at all the advantages. When a student doesn't want to be there, they don't have to be there, and they can watch your lecture whenever. So C will say, does your answer make sense? And I want to go through that again. Actually, I think I reworded it on your homework to why does your answer make sense? Because yes, of course your answer makes, well, your answer should. Because otherwise people say, no, my answer doesn't make sense. I don't know what I did. But so what should have happened is if you look at the K, the new K, my new K2 is greater. It increased. So if we compare it to the original numbers, this number, this K is much higher. So you must have increased the rate due to more jiggles and giggles. So more giggles and jiggles is great. So yeah, we got a higher temperature. We're at 25 versus 0. So it makes sense. Does that make sense? And we'll hold out for questions. If you want, you can try putting in your calculator. And if there's no questions, I'm gonna stop my recording.
Oh.
Go ahead.
I was wondering, I can't read the, it's kind of blurry for me on my computer. I can't read the word after rate. Oh, do.
Too.
Okay, yeah, there we go. My bad.
You
All right,
can use it. You can use any word you want there. In fact, there's more words there than I normally write on the board. I don't know why I'm writing incomplete sentences today. All right, I'm going to stop my share unless somebody else has a question. Or I'm going to stop recording.